Okay, hi everyone. Welcome to today's lecture. Apologies for a little bit of the delay in getting started. We were dealing with some technical issues of slides transferring from one place to another. Okay, so here's the plan for today. We are picking up on our discussion on recurrent neural networks. We will finish that module today. We have a couple of topics, beam search and generalization of element networks to LSTMs to look at. And then this will be the end of a module. Excuse me. This will be the end of a module on supervised learning. At this point of time, we are done with introducing everything that we want on language models and on rnns. And we will move on to a new module on reinforcement learning, which will be guest taught by Nirbhay, who I'll introduce in a bit. Just a quick recap on where we have been in this class. So we have looked at, for example, RNN, the vanilla RNNs or the concept of RNNs in this lecture so far. We have looked at the idea that there is a cell that we can think of, a recurrent unit of computation, and we have defined sort of the expression for that recurrent computation via what we claimed to be the sort of simplest formulation that you could do, which is take all the input at any given point of time, which is x and h, stack them together, pass them through a fully connected layer expressed by this matrix multiplication, add a bias term, and pass through a nonlinearity. And that is a recurrent expression for ht in terms of ht minus 1 and xt, which is the input. And we said, from this hidden state, you can decode yt as you wish, depending on an application. We showed you an example of this application, of this model on language modeling, or character level language modeling to be specific. And this now hopefully is making a lot more sense after Ishan's lecture on self-supervised learning, because here we are generating supervision for ourselves. This is an autoregressive model. The sequence at time t+1 serves as the ground truth to be predicted at time t. And this lets us predict what next character is coming in the sequence. We told you that at training time, what is input at time t is the ground truth entry from time t minus 1. And so this is in the machine learning literature or the deep learning literature sometimes called teacher forcing. And there is a train test discrepancy because at test time, you do not have the ground truth sequence. You do not have access to it. And so you resort to inference procedures like sampling, doing an argmax or beam search. And we told you sampling is just as the name suggests. At every point of time, you pass your scores through a softmax layer to get probabilities, sample from those probabilities to get a one-hot representation of the token or the character or the word that you decode depending on the application. And just repeat this at every point of time. We had told you that there are so sampling to argmax transition should be pretty easy to imagine. Instead of sampling, you can just take the argmax at every point of time. And we had told you we will tell you about beam search, and that time is today. So we'll tell you about beam search today. So that was a quick recap of where we were. Sorry, let me just go back. And today what we'll do is we'll tell you about beam search, but we'll tell you in the context of an application of image captioning. We'll tell you about multi-layer RNNs and a couple of generalizations to LSTMs. Okay, so quick sort of second example application, and we'll introduce beam search in this context, is neural image captioning, or taking in an input image X and producing an output Y, which is a sequence of tokens, Y1, Y2, till Y capital T. Each one of these tokens are words or tokens in a vocabulary. So, you describe an image with a sentence. And so this is, there's no sequence on the input, but there is a sequence on the output. And fairly simple models for this problem involve essentially embedding your image with a neural network. So you can take any convolutional neural network that that is competitive, VGGNet or ResNet. VGGNet these days isn't that popular, but when this kind of models were introduced, that's what was common then. And so you basically pass the image through a CNN. It has some last hidden layer representation. That is, you can call representation V. It lives in some R to the D, maybe, this is 512, let's say, and so, or 4096 in this case. So there's some hidden encoding of the image that we're embedding the entire image into. And then what we're going to do is we're just going to use that representation V as the, pass it through a linear layer and feed that as the starting representation for an RNN. And so there are a few different variants of, so if we're calling this representation V, there are a few different variants of these architectures. You can either pass V through a linear layer, and then this just becomes H0 that starts the RNN, or it's also common to use just modify the RNN update rules to, so for example, remember that we had tan H of W H H of HT minus 1 plus, and I apologize for my handwriting, I'm writing in a vertical surface because I'm trying to, XT, and there was a bias B H. So this was the update rule, and we can just modify it to include in this expression plus W V H times V. So we can just add an additional term to our update rule so that this vector V is present not just at the first timestamp, but at every timestamp. It's just being fed as input to the RNN. And you can imagine that this expression is the same as taking your XT and just augmenting it with V. And this is just a new input to the RNN. And so this can then typically what you have here are the input words starting with some start token. So 2 people and 2 horses, blah, blah, blah. And the model has to predict the probability for the next word. So notice this is a word level RNN, not a character level RNN. That's just a design choice. And from a sequence modeling perspective, it's just a different vocabulary and a different kind of sequence model. And so what the first word in, these are special tokens of start, and you also have a stop token. These are typically augmented into the vocabulary. The first word is always start, and then you ask your model to predict the next word and so on. Let me take a quick look at questions. There's a question about how do we quantify the test accuracy for RNN, kind of yes or no for each character predicted. Yeah, that's a good question. So when you do character level language modeling, you can look at log likelihoods of the produced sequences, and so that you can know the quality of the sequences produced, and you can use log likelihoods to compare 2 different models. But it's not it doesn't tell you it doesn't tell you in some sense metrics like fluency, like are the sentences that you're producing fluent or grammatically correct. You can't actually do yes, no for each character predicted if you are generating the entire sequence, because you don't know whether this sequence may not be present in your data set, but it may be a valid sequence. And so what can be done is if you feed in a partial sequence, you can test whether the next character it gives you is the right character. But this runs into problems when you have multimodality in your data set. So if partial inputs can lead to 2 different outputs, then it becomes difficult. So language modeling tends to rely on human evaluation for these. How is this architecture, I imagine this being image captioning, different from the attention-based encoder-decoder that we saw? Can V be something similar to the context? Yes. So V is something similar to the context in that. This is a simple version. This does not have any attention. This is encoding the entire image once and then feeding it. And so those architectures are generalizations. I just wanted to repeat that so that we had this architecture in front of us. Okay. So what I wanted to show is the use of this architecture to explain beam search. And so I will switch to a demo of beam search because I find this particularly useful. So the link is in the slides, and I've already pulled the demo slide up. This is a website called Diverse Beam Search. It's an algorithm that my students and I developed a few years ago. It's a generalization of beam search. I am not going to talk about the diverse part. I'm just going to teach you beam search, the vanilla algorithm. And so, we've uploaded an image to this website. I've already done this just to get save time and get started. And what beam search is going to do is that there is an input image X. We've converted that into the vector. So now, from an rnns perspective, what a beam search is going to do? Notice on the x-axis is time, or iterations, indicator of time. And so what we're going to do is, instead of doing argmax or sampling, beam search tries to keep track of some beam width length hypotheses or partial sequences. There's a parameter here called number of beams. You'll notice it's on the screen. This is a hyperparameter in the algorithm, and we have chosen it to be 5 for now. I will talk about the effect of this parameter. And the effect of this parameter is that we actually, instead of maintaining a single sample or a single argmax, we sort the vocabulary to give us the top 5 or top B most likely samples, most likely tokens at this point. So you notice that the model wants to start this image out with 3, 2, 4, and several. These are in sorted descending order of log probability of the token given the input. We take the top B of them, and so notice there were vocabulary number of things, and vocabulary might be 10,000. We've kept only the top B of them, and for the top B that we've kept, for each one of them, we are going to expand the sequence out to the next time, out to the entire vocabulary length, and keep top B of them. So 3 people, 3 men, 3 riders, 3 horses, 3 young, and so on. So this is now a partial sequence extended to time 2. A group, a couple, a man, a few, a number, 2 people, 2 men, 2 horses, 2 riders, 2 women, and so on. And so these are partial sequences now, B times B. So there are B squared partial sequences, and we're going to sort it to reduce it to top B again. So we're going to keep top B of these partial sequences. Some branches die. So 4 was never expanded because so for each partial sequence, we can add up the log probabilities of each token, and that's giving us the log probability of that sequence, because adding log probability is the same as multiplying the conditional probabilities, and therefore you get the probability of the sequence. And sorting by that log probability tells us that here the top B most likely hypothesis: 3 people, 3 men, a group, 2 people, 2 men. You can draw analogies of this to graph search. This is a hybrid between breadth first and depth first search, and we just keep repeating this at every time step. So 3 people riding, 3 people on, 3 people ride, and so on. So there are B expansions of each of these top B partial sequences, and then the algorithm just proceeds in this manner till a stop token is hit. And so notice that it's nicely exploring these 2 paths. 3 people are riding horses on a beach, and then there's an end token. A group of people riding horses in the water, on the beach, riding horses on the beach, riding horses on a sandy beach, and so on. So there's a nice little search tree that's being explored here. And at some point, end tokens are reached, and that's when beam search stops in all of these cases. And so we get this as a output. These are the top B beams that we have produced for this algorithm, and they're naturally sorted by log probabilities. And in your homework, what you're doing is you're proving a nice sort of understanding of stopping criteria for beam search, about when we might stop if we, for example, do not have these end tokens. Okay, so that was beam search. All right, so, and this image captioning kind of works. You get these really interesting examples of, a cat sitting in a suitcase on the floor, a cat is sitting on a tree in a branch, a dog is running on the grass with a frisbee, a white teddy bear sitting in the grass. These things are beginning to be mature. Where they still tend to fail are atypical images. So you will often find the model predicting or hallucinating things that aren't happening. So a woman is holding a cat in her hand, and it's because the texture of the fur is probably reminiscent, being mapped to a particular category. A person is holding a computer mouse in the desk. That's not a mouse. A woman is standing on the beach holding a surfboard, and it's because upside down images or people doing handstands isn't particularly common, and so this may just never have been observed. And a bird is perched on a tree branch. It's likely that the spider images are just not there in the data set. So what you find in image captioning images are that it tends to describe common or prototypical images well, and not atypical images. Okay. So let's take a look now. Now that we've understood beam search, let's take a look at a couple of other things that we want to cover about multilayer RNNs and LSTMs in particular. So just like there are single layer RNNs, there are multi-layer RNNs. So in RNNs, we can talk about depth in the vertical direction. And so you can think of this as layer L and this at time t, and so we can generalize our notion of h at L time t, and so you can think of this as, if this is xt, you can think of this as h0 t. So this is the hidden state at zero, at the zeroth depth. This is producing h1 at time t. This is producing h2 at time t, all the way till y at time t. And so we can just with that notation, write this general expression that the hidden activation or the hidden cell at any time is just concatenate both. So consider this is h L at time t. It has two inputs, one from h L minus 1 at time t and one from h L at t minus 1. And so we can just concatenate both of them into a vector, pass them through a matrix, and do a tan h, and plus obviously the bias. And this is just a generalization of a single layer RNN to multi-layer RNN. How many layers should you use? That's typically a model selection question. You'd have to try a few and pick this via cross-validation. Okay. One problem that becomes particularly important and particularly pathological in just vanilla RNNs, forget whether they're deep or single layer, is this notion of gradient flow and problems with gradient flow. And it comes from this observation that we are in order to produce ht from ht minus 1, we can write down the cell or the computational graph of ht in terms of ht minus 1 as a stacking and a matrix multiplication operation. So this is something that we've been saying this entire time, that you can take ht minus 1, stack xt, and that can give you this matrix multiplication by w, that can give you pass through a tan h, that can give you ht minus 1. But really, if you think about during back propagation, what's going to happen, there is a tan h operation happening, and that part is pretty easy. That's going to lead to this Jacobian that is going to be diagonal. The Jacobian of matrix multiplication is itself. We've done this in earlier lectures, that the Jacobian in this red arrow is w itself, and so you just multiply the gradient on the left, and that's the back propagation operation. This leads to a particular problem, that we are multiplying by the same matrix when we have unrolling happening. We are multiplying by the same matrix over and over again. And one way of sort of simplifying this problem is, imagine if x's were not present in this RNN. So if there was only h's that were being propagated, so there's no stacking happening, And imagine if there was, just for the sake of simplicity, imagine if none of the tan H's were present either. So let's assume none of these things are present. So really all that's happening is you're writing down H1 is equal to W times H0. You're writing down H2 is equal to W times H1 and so on. Let's say that's the simple operation that's happening in all of these things. When you try to compute the partial, when you try to compute the partial of H capital T in terms of H0, you realize that chain rule tells you that you will get T with respect to T minus 1 multiplied by H1 with respect to H0. Each one of these, if this is the expression that's happening, is W. So we just keep multiplying by W over and over again. And so really we get W to the power of T plus 1, right? So you get some exponential power of W. And W in this case is a matrix, but let's make our life simple and let's assume H is one-dimensional. And so W is a scalar. So if H sub T is R to the 1, W is also R to the 1, then you just get this scalar W with this to the power of T plus 1. And then it becomes pretty easy to understand what's going to happen here. If you have a scalar and you multiply it over and over again by some power T, if that scalar value is greater than 1, you get this blow up of the gradients because now they're suddenly exponentially large. If the scalar value is less than 1, you get these things going to 0. And yes, I'm ignoring the sign of W in this analysis, but I'm just trying to give an intuition and keep that simple. You can carefully handle the sign in this expression as well, depending on the parity of T and odd and evenness of T. But that doesn't change the fact that you get this either blow up of the gradients or shrinking down to 0, depending on whether W is greater than or 0, greater than 1 or less than 1. And this analysis is simple if W is a scalar, but if W is a vector, you can still do this analysis. You just have to look at the eigen decomposition of W and realize what's going to happen when you multiply matrices to the eigenvectors. When you multiply matrices over and over again, what happens to the eigen decomposition? And this is kind of what we've told you to analyze and derive in a homework problem. But really, you will run into this problem that if the largest singular value of W is greater than 1, you will get what are called exploding gradients. If the largest singular value is less than 1, you will get what are called vanishing gradients. Exploding, as in the magnitude of the partial derivatives, becomes increasingly large, exponential in the length of the sequence. Vanishing, also vanishing to 0. One common solution for exploding gradients is called gradient clipping. This is a common trick that you'll find in implementations, which is just check for the gradient norm. And if the gradient norm is greater than some threshold, then scale the gradients by the norm of the gradient by this threshold. And so this is called gradient clipping. For vanishing gradients, what is much more common is to change the RNN architecture, and that's exactly what we're going to show you today. Vanilla RNNs have a particular problem with vanishing gradients that LSTMs try to overcome. So vanilla RNNs have a single variable HT that is written by this recursive iterative update rule. LSTMs have 4 internal variables that are written by this update rule. So you still do the stacking, you still do a matrix multiplication, and then there are sometimes you do sigmoids and sometimes you do tan H's, and then there's an update rule. It seems fairly arbitrary and sophisticated. I can at least tell you that it's not that sophisticated, and hopefully you'll understand that in the next few slides. It will continue to feel arbitrary, and we'll try to address that in a few slides. Okay, so let's dive deeper into what's going on into these equations. So I find that the best way to understand these equations is with this illustration from Chris Ola. These are a wonderful set of illustrations on his blog, and he's also one of the co-creators of the distill.pub series of papers of that journal. And so I encourage you to check this out. The way to think of this particular LSTM cell is that, just like a vanilla RNN or an Elman network, there is an input XT and there's an output HT. There's a hidden variable HT which is passed on to both in time and in depth. But in addition to just HT, we have a new variable that we are going to call cell state or cell memory. So we now are going to distinguish between CT and HT. HT still exists. We'll call HT the hidden state, and CT will call the cell state or cell memory in the context of LSTMs. CT is going to be internal to this cell. So in fact, part of the notation is somewhat wrong because it's actually CT that's hidden from the outside world. But we'll just deal with this. This is just the way things are. But CT is a similar object. It's R to the some dimension D, maybe 512. Typically, this is kept the same dimensionality as HT. So HT lives in some dimensional space. RT lives in some dimensional space. CT and HT both live in some RD. And what we're going to do is we're going to interpret every dimension of CT. So the first dimension, second dimension, as a particular bit of information. That's how we're going to view CT. And why is it going to be a bit of information? It's a continuous value. Well, because as you'll see, we will use tanh to store information along each coordinate. And so we can view the output of tanh as a particular bit. So tanh is not binary. It varies from -1 to +1, but you can view it as a soft bit, if you will. And the question we're going to ask is, we're going to say CT is a vector, and we're getting a hidden vector as input. This was our memory. This was our cell state. What we're going to ask is that we're going to define a gate called forget gate. F is going to be shorthand for forget gate. And we're going to ask the question, in the dimension D, in the dth dimension, should we continue to remember this bit of information or not? We were remembering this bit of information over time. Should we continue to remember it or not? And the way we're going to answer that question, yes, no, is we're going to take our source of information right now. We have HT-1, we have XT. We're going to pass that, concatenate them, pass them through a matrix multiplication, add a bias, pass it through a sigmoid, not a tanh. Notice this is a sigmoid now. And we're going to interpret the output of this sigmoid, between 0 and 1, as a soft bit for whether we should forget this dimension or not. So FT is the same dimension, this is RD as well, the same dimension as HT, and we're going to interpret every coordinate of FT as whether we want to forget this particular bit or not. We're going to play this same trick with a second variable IT, and IT tells us whether we should update this bit of information or not. So the same trick, concatenate HT-1, XT, pass it through a second matrix WI, add a bias, pass that through a sigmoid. So now IT also lives in some R to the D, and we're going to interpret every bit of or every dimension of IT as telling us a soft probability of whether we should remember, whether we should update this dimension or not in this iteration. And if we're going to update it, what should we update it with? And so we're going to construct a candidate memory cell. So C tilde is going to be a candidate replacement for CT. And we're going to construct it, at this point, this has become mechanistic, right? We have some input, HT-1, XT, matrix multiplication, bias, tanh. Notice this is a tanh because this is the entry that will go into this to update this cell. So we're going to make this between +1 and -1. And the way we're actually going to update is to say, forget that, memorize this. And so FT, which is a vector of sigmoid values between 0 and 1, is going to element-wise multiply this candidate CT-1. And then we will add, so this is the forgetting part. So if this value is set to 0, then you forget this particular coordinate. And this is the remembering part. So if this value is set to, so if there's a 1 here and a 0 here, you forget this coordinate and you remember, you add in the new candidate CT tilde value and in this coordinate. And so realize that this is a bit over parameterized. We could have said, IT is 1 minus FT. We could have just done that while we have to have separate things. Those are variants of LSTMs that exist. And ultimately, there is a fourth thing, which is, should we output this bit of information to deeper layers? So HT is what gets exposed to deeper layers. CT never gets exposed to the outside world. CT just continues as the persistent memory of the cell. And so OT is again a vector in R to the D, and we're going to treat every bit of or every dimension of OT as a soft bit telling us whether or not we should expose HT to the outside world. And so if this dimension of OT is close to 1, then this output of CT will actually get exposed. If it is not close to 1, then if this is 0, then it will not get exposed. And so that is the inner workings of each of the 4 variables in an LSTM. And one of the key problems that LSTM solve is that you have this cell memory that undergoes large, essentially an addition operation and an element-wise product. There is no matrix multiplication that happens. So there's a diagonal matrix that multiplies it, which is the element-wise product, but there's no full matrix that ever multiplies it. And this right here is why we are able to overcome the vanishing gradient problems. Because if you notice that anytime you're doing summation or an element-wise multiplication, that does not lead to repeated matrix multiplications. Repeated summations, notice, never have any problems because summations during backprop are let the gradients pass through. They are distributors in the backprop. And so because there's no matrix multiplication, we've overcome that problem of gradient decay. And so this is the uninterrupted flow of gradients across time. And in that sense, this is very similar to skip connections in ResNets, where one of the arguments for skip connections is uninterrupted gradient flow. So this is what an LSTM cell is. It appears, so now hopefully you understand the intuition behind them, but that doesn't mean that they are not arbitrary. They appear somewhat arbitrary, but they are a design choice, and they tend to work well. There are a number of variants of LSTMs. So you can, for example, not just consider HT minus 1 and XT, but also add CT minus 1 as input to each of these gates. And so that means that you're adding an additional line as a connection between CT minus 1. So notice that in our previous design, CT was operating essentially unchecked, and this is what was giving it the gradient flow. Now we are adding a bunch of additional paths, and so it's unlikely for CT to get updated because of that, but we could add this. Another LSTM variant is to have coupled gates. That's what I was mentioning. So you don't have an forget gate and an input gate. You just have a forget and a 1 minus forget gate. So if you are going to forget, then you remember something else from the candidate, and if you're not going to forget, then you do not add something from the candidate. And this is just a way of reducing parameters. And GRUs are a specific variant with a different set of update rules and equations. We will not go into too much details of GRUs because it doesn't really matter. These are specific design choices that people found useful in general. But the way to think about this is that there's what you want to do is you want some way of making sure gradient flow happens, which is an optimization concern, but you also want some sort of persistent memory which can be recurrently updated in a cell. And over time, what has happened is that people have started applying neural architecture search, and they've started coming up with other variants that are found by algorithms rather than by humans. We will have an entire lecture towards the end of the semester on neural architecture search, where algorithms search for these cells that find update rules and other architecture design choices. And a number of other choices also work consistently well. Okay. So that's the summary for LSTMs and RNNs. We are now done with this entire module on recurrent neural networks. And I'll take a few questions now, and after this is when I'll hand it over to Nirbhay. Okay, can we add forget gates to ResNets as skip connections don't forget anything? Will it improve performance of ResNets? Interesting question. So instead of adding everything, you just have a element-wise multiplier to the x plus to the skip connection. Yeah, I am not aware of any published work that tries this, but it's worth trying. I think it's an interesting thought. Try it. Okay, I'm not seeing any additional questions. So let me just say a few words about where we are in the class. We at this point are done with supervised learning as a module, which covers both CNNs and RNNs and fully connected layers. We have started looking at weaker forms of supervision, which is what Ishan covered in the last lecture. And in the rest of today's lecture and the next two lectures, we are moving into a new module called reinforcement learning that Nirbhay will cover. So let me just introduce our speaker. Nirbhay is a PhD student in the School of Interactive Computing at Georgia Tech. His research interests are in reinforcement learning and in information theory, so he works in this area. Nirbhay has also been a TA for the deep learning class twice. He's given these lectures on deep learning on reinforcement learning in this class before. So I'm really looking forward to this. One of the reasons why we have guest lectures from PhD students is I want all of you to begin to feel comfortable in identifying who are the people working in these areas and who to reach out for, and just generally, expand your network of connections and know that you can reach out to some of these people and for asking information about these topics. So with that, I'll hand it over to you, Nirbhay. Go ahead.
Yeah, thank you, Dhruv. Let me start sharing my screen.
Okay.
I'm turning on annotations. Okay, is this visible to everyone?
Yeah.
Yeah, okay. So hi, I'm Nirbhay, and today we're going to talk about this area of research called reinforcement learning, which is very popular in recent years and which I'm very excited to teach about. So yeah, let's dive in. So by now you guys have seen many types of learning so far. You have seen supervised learning, in which you have a data set of inputs and labels, and the job is usually to produce a mapping from input to output, which is from your data points X to your labels Y. And you've seen tasks such as classification, where you want to, let's say, classify an image into categories like cat or dog. And in the last lecture by Ishan, you've seen unsupervised learning, where you have just a large amount of data which is unlabeled, and you're trying to either learn some lower level representation of the data to understand it better or to use it in some downstream task. And today, we're going to talk about something slightly different. We're going to talk about reinforcement learning, in which we are supposed to make a sequence of decisions, which is kind of similar to what you've seen in RNNs. But instead of supervision in the form of supervised learning, you're going to get supervision in the form of evaluative feedback or reward. So I'm going to talk about more on this in the next slide. So what is reinforcement learning? In one sentence, I would describe it as sequential decision making in an environment with evaluative feedback. So let's first talk about what this environment is. We have this agent which lives in an environment which can be thought of as the world. The agent interacts with the environment by taking actions, which are also called responses, or how the agent controls itself. And the environment tells the agent how it is affected by these actions in the form of the state, the stimulus which the agent perceives, or what the situation the environment is currently in. And in addition to that, it also tells the agent how well it's doing by giving it some reward, gain, payoff, or some cost of operation. Now, this environment may be unknown, it may be nonlinear, it may be very, very stochastic and complex. Think of the worst case as this being a real robot deployed in the real world, which is the environment in that case. And the agent's job in this setup is to learn a policy, which is basically a mapping from states to actions. So it needs to learn how to take actions to affect the environment. And its objective is to maximize its payoff, or the long-term payoff which it will get eventually from taking these actions. And now that we know what the environment is, let's talk more about what sequential decision-making and evaluative feedback are. So evaluative feedback means that the agent is supposed to pick an action and then receive a reward which can be positive or negative depending on what action was chosen. So this is in contrast to supervision, where for every data point X, you make a prediction or a decision, and you're given the correct decision or label Y. But here you're not given what the correct label or decision is supposed to be. You're just given feedback on what label you predicted. So that is the difference between evaluative feedback and supervised learning. And you see in sequential decision making several times right now in rnns and LSTMs. And that is just, it means that you have to plan and execute actions over a sequence of states now. And another challenge is that reward may be delayed. So maybe after taking several actions, at the very end, you get some reward signal which you wanted in the first place. So there may be very long and delayed rewards. Now let's talk more about what the interaction protocol is for reinforcement learning. So you have this agent here, and at every time step, let's call it T, the agent is supposed to receive an observation from the world, which is OT. It is supposed to execute an action AT, and that action is supposed to affect the environment in the following way. It'll the environment will take the action and it will produce a new observation or the next state of the environment OT plus 1, and it will emit a scalar reward RT plus 1, which the agent will take as feedback. Okay. So, and one of this, let me just quickly point out what the signature challenges in reinforcement learning are. The first I've already mentioned is evaluative feedback means that you have to do a lot of trial and error to find the right action, because you've never been told what the right action would be at every state. The other is that the feedback may be delayed, yeah.
Can I just, so I just wanted to add a quick point here in the examples, in the context of examples that you've already seen. So imagine if we were still doing language modeling with character RNNs, let's say, so let's say our data set is HELL O, and so you start with HELL, and let's say instead of giving you supervision for O, I just told you, keep making guesses. I'll tell you if you get it right or not. So you make a prediction after HELL, and let's say you say A, and I, keep giving you feedback like go fish, that's not the right answer. And you say, okay, what about B? Go fish, that's not the right answer. And that is what trial and error here is referring to, that I'm not telling you what the right action supervision is. I will just evaluate the action that your agent ends up taking. And in this HELLO example, it feels contrived, and it's actually an easier case because you can condition on exactly the 4 HELLs, and you can make multiple guesses about, the vocabulary, and that's corresponding to the, space of actions. And you feel like you can just enumerate over all of them, and you've just added a multiplicative factor, the size of the vocabulary. But imagine if the world never stood still. Like if you said HELLA, I said, no, that's not the right answer, but now we've sort of moved on. The world is now at HELLA, and now make your next guess about what comes after this. So that's the sort of problem with RL. It's a much richer abstraction for realistic problems in the world, but it has a much weaker form of supervision. You just get told feedback about what you did, not about what you could have done or what the right thing to have done was. Back to you, Nirbhay.
Yeah, precisely. Thanks, Dhruv. Yeah. So the second thing is, which I've mentioned just a few slides before, is that the feedback is maybe delayed in the sense that you get rewards only after taking several actions, and down the road, you'll see what effect the actions caused. The other challenge is non-stationarity, which basically means that data distribution of visited states changes with the policy. So what I mean by that is when I make a small change to my policy, suddenly now that policy is going to take very different actions. It's going to visit very different states. And the states which are going to be visited is going to be the data set or data distribution which I'm going to look at to update my policy. So this shift in my data distribution as my policy changes is going to be very problematic, and something we're going to address in the later lectures. And the last challenge is that the fleeting nature of time and online data. It may just be that there may be some states which you never see again in the entire life of the agent. So it's like you either make the right decision right now, or you're never able to make the right decision at the same state again ever in the trajectory. So there are a lot of challenges in RL, but fear not, we're going to look at how we can solve some of these challenges in this lecture. So
Yeah,
let me give some examples of.
Sorry, could you go back, Nirbhay? Just to expand, imagine if the way you did language modeling is that you produced a sequence of characters, and I waited till you produced the entire sequence, and then I told you that then I gave you a score for that sequence, and let's say that score was binary, whether that sequence comes from forms a valid word or not. Then that would be both evaluative feedback, because I'm not telling you how to form words. It's delayed feedback in the sense that I don't give you feedback at every character. I just wait for the entire sequence to finish and then I tell you things. It's non-stationary in the sense that in the sense that the supervision is a function of the data that you are generating. And so if you change your policy, if you start producing different kinds of words, the supervision, or not supervision, but the reward for that will change. And it's fleeting nature of online data in the sense that imagine if you could never store your previous action. So every time you produced a sequence, you could never go back into that sequence, and then you just have to start all over again. And so that's the instantiation of these 4 challenges.
Yeah. So let's now look at some examples of what problems can be cast into a reinforcement learning task. So one is robot locomotion. So in this case, and let me just tell you about how this environment would be in the setup of reinforcement learning. Your objective in this case would be to make the robot move forward. So in the left, it can be this robot which has all of these joints, the head, 2 arms and limbs. And in this case, it's a tiny ant which has 4 limbs and 4 joints. The state is basically the angle and position of the joints of each robot. The action can be the torque applied to rotate these joints. And the reward can be +1 at each time step upright and moving forward. And this is just a signal which will promote the agent to move forward and control itself. So in this case, I would call this a very hard control task, because you have to learn to move every single joint of the robot such that the robot itself moves. And you can see that this will be quite a hard challenge to solve. But in recent times, people have solved this challenge using reinforcement learning. And some more examples are Atari games, in which case the observation is now, instead of some simple sequence of vectors, your observations are entire images. So what you see right now is the game screen, and that is also what the agent sees. And so basically the state is the raw pixel inputs of the game state. And the action is basically whatever the game defines as its controls. It can be left, right, up, down, or whatever each Atari game defines as actions. And the reward is quite simple now. It's just what is the score in your game. Like the score is basically usually on the top of the screen in every game. It'll tell you how well you're performing. And the one reward can be basically how much your score increases or decreases at each time step in this game. And another example is something you all may have seen. It's games like chess or Go, in which the objective is just to defeat the opponent. The state is the pieces of the board, which you can see right now. The action is where to put the next piece down. And the reward is now significantly delayed. It's +1 if you win at the end of the game, or 0 otherwise. So now you have to take probably like thousands of actions before you actually get any reward or any indication of whether those actions were good or bad. So you can see that this is a very challenging task, given that the reward is so sparse. Now, for today's lecture, we're going to talk about some theoretical background for reinforcement learning. And I'm going to introduce Markov decision processes. So what is an MDP, or Markov decision process? It is a theoretical framework which is underlying reinforcement learning. It is defined in the following way. You have S, which is the set of possible states the agent can be in, or the world can be in. You have A, which is the set of actions the agent can take. And you have these reward distributions and transition probability distributions. The reward distribution basically says what is the probability of distribution of getting a reward given a state and action has been chosen by the agent. And the transition probability is basically how the world works, or how the world will change based on the agent taking action A at state S. And this gamma is a discount factor, which I'm going to talk more about later. But for now, I'm just going to mention that it's a way of telling how to emphasize rewards rewards which are going to come sooner, as opposed to rewards which you're going to get towards a later stage. And the protocol for using an MDP is going to be as follows. You're going to, with the interaction strategy we saw before, an agent is basically going to interact in the form of a trajectory, which is a sequence of states, actions, rewards, and next states. So this is going to be the unit of our trajectory. And the reason it's called a Markov decision process is because we're going to use the Markov property, which is basically saying that the current state completely characterizes the state of the environment. And what this means is that the most recent observation is going to completely describe what the environment is. And in practice, what this means is that the transition probability, which we just saw, the probability that a next state is reached, given that a state and action has been chosen, this does not depend on the history of the trajectory. So whatever happened before state ST and action AT was chosen, that does not matter. The distribution only depends on the current state and the current action. And now I'm going to talk about two kinds of MDPs. One is a fully observed MDP, where the agent receives or knows the entire state of the environment at time step T. An example of this is chess and Go, which we have seen before. And a partially observed MDP, on the other hand, is when the agent only perceives a partial observation OT of the true state ST of the environment at times T. Using and this agent will typically preserve the history. Since it doesn't know the true state of the environment, it's going to preserve the history of the states it's seen, usually with an RNN. So we'll take a look at more about how to use RNNs in RL soon in the next lecture. And an example of this can be games like poker, where you only know or see the current hand which you have dealt. You don't know what other people have in their hand. Or it can be first-person games like Doom. And people have done a lot of research specifically in Doom, where they want to learn how an agent can observe the first-person view of the game and predict actions such that they can win the game, basically. But for now, in today's lectures, at least for when we look at studying and solving MDPs, we're going to assume that the MDP is going to be fully observed. And now let's talk about how MDPs are going to be used in reinforcement learning. What does it have to do? What do these things have to do with reinforcement learning? So RL is particularly challenging because we're going to assume an underlying MDP without knowledge of the transition probability T and the reward distribution R. So what this means is that when I don't know the reward function, the evaluative feedback comes into play, which means that I need to do trial and error to know eventually what is the right decision to make that will give me a high reward. And not knowing the transition probability means that I don't know how the world works, and I'm going to have to do trial and error to understand or get a better understanding of what effects my actions have on the environment. But let's say for now that we have access to the transition distribution T and the reward distribution R. We're going to ask the question, given this information, can we solve the MDP? As in, can we get the optimal policy or the best policy which will produce the best possible reward? So we're going to assume for this lecture that we know the true reward and transition distribution. So there's no evaluative feedback for now, and we know how the world works. So we know exactly how our actions are going to affect the environment. And even with these assumptions, we're going to see how algorithms can be used to solve MDPs. And then we're going to use those algorithms eventually and transfer them to the reinforcement learning setup when we don't know the T and R.
By the way, just as an example, in the context of, for example, chess or Go, knowing how the world works is equivalent to assuming that you know the rules of the game. So you know where pieces can be placed. You know what will happen when you place a piece somewhere, whether it kills another piece or not. So knowing how the world works is a reasonable assumption under certain conditions. For example, closed games like the games of chess and Go. However, it is not a reasonable assumption in all possible cases. For example, if you try to pose a robotics problem like navigation or manipulation of objects as a reinforcement learning problem, like I'm trying to teach a robot to pick a mug up and place it from point A to point B. In that case, knowing how the world works is assuming that you have a perfect physical replica of the world. You have a perfect simulator of the world inside the robot's head. So the robot knows, for example, that when it grasps the mug with certain force, if it does not grasp it with enough force, that the mug can slip, and that forces have implications on things, on what's going to happen in the world. Those assumptions are unrealistic because perfect physics simulators of the world don't exist. We just don't have those kinds of things built in. So that's what this assumption means in different contexts.
Okay. So now with these two assumptions that we know the reward function and the transition function, let's see how we can solve the MDP. Let's take an example of this grid world MDP. In this case, the agent lives in a 2D grid world as shown here. The agent can be is this blue triangle. The agent state is basically the 2D coordinates in this grid. So it's basically now at 2, 3. The agent's action is basically the cardinal directions, north, south, east, and west. The rewards are only obtained at these two absorbing states. So by absorbing, I mean that the agent's trajectory terminates when it reaches either this state or this state. And now, just with this, looking at this MDP, can someone tell me what is the optimal set of actions to take?
It usually takes 10 seconds or so. There's a lag.
Yeah.
The question on the table is, what should this agent do in this world? Yeah. And so
should it go east, west, north, south? What actions can lead it? Be taken for it to reach get a high reward?
Yeah, you have one answer that we received on chat. Right, right, east, east.
Yep. Okay. So yeah, that was quite a simple, I guess, first question that you can, if you just take 2 right actions or 2 east actions, you will eventually reach the +1 state. But now let's say that walls, like the actions always do not go as planned. Now there's some stochasticity in the next state given the action. So what I mean by that is there's a 20% chance that the agent drifts one cell left or right of the direction of motion. So when it wants to go forward, there's a 10% chance that it will go right and a 10% chance that it will go left. So now if I take the same actions, there is some probability that I'll not end up at this state. So now what will happen is that just taking the optimal set of actions east and east will not be the right thing to do. What the agent will have to do is first take an action east and get to this state at time step 1. And then what can happen is that with some probability, it may reach this state instead. And depending on whether it reached this state or this state, it will have to choose the next action carefully. So if it's at this state, it can just choose the right action, and with 80% probability or 90% probability, it will reach the +1 state. That's good. And when it's at this state, it'll have to recover, try to go back up, and then go to the right state. So you can see this is an example of where even when you know the transition and reward functions, even if you know what the right thing to do is, you may still not end up having high reward just because of the noise or the stochasticity in the environment. And the way we're going to solve this environment is basically by doing by looking at algorithms which can ask what is the right action to take at every single state. So what I can tell, one way of describing what is the right set of actions to take can be just a tensor, which is basically the state space, which I've seen here. And every element in that tensor will basically say what is the best action to take at that state. So let's say the agent was here instead. What is the best action to take? Should I go up or right? And let's say I'm at this state. What is the best action to take? Should I go up, left, or right? So now this specification of what action to take at a particular state is going to be called a policy. So, what I mean by solving an MDP is going to be find the best policy or the optimal policy which can maximize the rewards which I'm going to get eventually. So formally, a policy is just a mapping from states to actions. And from the example we saw before, can someone tell me what is the dimensionality of my policy if I represent it as a tensor in memory, if it's a deterministic policy? So for every state, my policy specifies one action. Then what will be the dimensions of my policy as a tensor? I'm going to wait for a few seconds.
And I guess as said on the slide, the number of states is n and the number of actions is m.
Yeah, sorry about that. Yeah. So given that these variables are what you know, n is the number of states and m is the number of actions, what is the dimensionality of the policy?
We have guess number 1, which is n.
Yes.
Maybe you can. Yeah.
That is correct. So for this case, it will be just n, and if it's a tensor, it's just going to be n by 1. That's one way of representing the policy, because for every state, this tensor is going to tell me what action should I be producing at that state. That's going to be fully specifying the policy in the form of a tensor in memory. However, if my policy is now stochastic, I see that I have only 2 minutes left, so let me just quickly wrap this slide up. If my policy is stochastic, what I mean by that is for every single state, I'm going to now define a distribution of all possible actions in my set. If this is the representation of my policy, what will be the dimensionality of my tensor? Again, note that we have a discrete set of states and a discrete set of actions, n and m.
We had a few guesses from the previous one for deterministic, which was some guesses were n times m and some guesses were n raised to power m. Maybe after, and we have more guesses coming in n times m now. N times m.
Yes.
N times m. Yeah.
So the right answer is n times m. And why is this the case? Because let's say you are at a particular state, which I'm indexing by this row of this tensor. For that state, I want to specify fully the probability distribution over actions. And this distribution is over a discrete set of m actions. So what I need to specify this is m probability values. So one row of this policy will be m probability values, and I need to do this for every single state. So my tensor for pi will end up being of shape n by m.
Yep, that makes sense. And can you, just so that people are clear, absolutely clear on this, can you say why it is not n to the m, n raised to power m?
I don't even know what n raised to the power m would mean. Like, I think that would be like the combinatorics perspective, like that you need to specify for all states and actions what is the.
Yeah, I guess one way of, so why something is not something is a hard explanation to give.
It's a hard explanation. I don't know why it would be n power m.
Maybe one way of, one explanation for that would be there are no interaction between the states, right? For every, it's a mapping from a state to action. So there does not need we never need to consider any interaction between states. And that's why there's no product interaction,
exactly
happening.
Yeah, exactly. And so let me just wrap this up.
Sorry, just one last thing on this slide. N raised to power m would be the total number of policies. Would that be the total number of policies for the deterministic case?
I have not actually thought about that, but I think that it would involve exponential expressions. So that seems to be something close to it. There will be an exponential number of possible policies, given that a policy is of size n by m.
Yeah, I think I also hesitate from doing this on the spot, but I think m raised to power n would be the total number of policies, because you have n slots to fill, and what you fill it with are the number of actions, and so every filling of those slots gives you one setting of policies. So m raised to n would be the total number of policies.
In the deterministic case, yes, but I think since stochastic policies have real valued probabilities, they'll be infinite. But in the deterministic case, I guess that's correct. It'll be that will be the correct answer for deterministic policies. Yeah. So yeah, just from that exercise, we know that there are an exponential number of deterministic policies. So finding a good policy is going to be a hard task, and which gives us more motivation for looking at algorithms which can help us find this optimal policy, even for MDPs. And yeah, this is the last part. I'm just going to end after this. So now, given that we know what a policy is, it is formally defined as a mapping from states to actions or states to distribution over actions. We're going to ask the question, what is a good policy? And how we're going to measure the goodness of a policy is by either how much reward it gets now, or it could be the sum of the future rewards it gets. Instead of these two, what we're going to now see is a new term, which is called discounted sum of future rewards, which is going to use the definition of gamma, which we saw earlier in the definition of MDPs, which is going to say that I care about rewards, but the rewards are going to be worth less to me as I get them in the future. So if I'm getting a reward now, it's going to be worth 1 point to me. If I get the reward later, it's going to be worth less to eventually do actions to get that reward. And and one analogy of this can be, let's say you're in a game where the reward is some gem which is disintegrating. So you have to reach it as soon as possible. So if you take a very long time to reach it, it will be gone by the time you reach it. So it's better to reach it quickly than reach it later on. This can be one way of indicating how you want the rewards to be prioritized by the agent in getting a good policy. So let's end at this. And in the next lecture, I'm going to talk about value functions, and which are basically going to characterize how good are states and actions in a particular MDP. And we're going to look at also algorithms to solve MDPs, such as value iteration.